Hello everyone, my name is Nathan Bayo. I'm a master student in computer science at the University of the Western Cape. In this video, I present our paper entitled Environment 4.0 and IoT-based pollution monitoring model. To give you an overview of our work, this presentation is presented according to the following plan. We will start with an introduction, follow-up of the presentation, the environment model 4.0 based on pollution. Then we will provide the evaluation of the performance of the system. Finally, we will end with the conclusion and future prospects. Pollution, noise, air, and water is one of the greatest health risks and also one of the greatest scourges of our time that is causing significant increase in the rate of morbidity and mortality in developing countries. To measure pollutant levels, some countries have deployed pollution networks using professional monitoring stations located at pre-established locations in cities. However, these professional devices are installed in limited numbers and certain locations of a city, therefore do not cover the entire city, hence a visibility gap that is generally found in air pollution maps around the world. For example, the South African Air Quality Information System provides information on air quality based on air pollution stations located in only 20 of the 54 municipalities of the Western Cape. While many researchers have been working on the design and development of environmental monitoring systems based on IoT, each solution differs by the type of IoT devices used, the protocol used to enable communication between these IoT devices, the data processing method, the cost of development and devices, the energy consumption of the end devices. The key challenge addressed by all these studies was to set up a participatory surveillance system using alternative technologies, complementary systems, and strategies to bridge the visibility gap left by professional pollution stations deployed in cities. This paper proposes a pollution monitoring model designed within the Environment 4.0 project that showcases how 4th Industrial Revolution can fill such visibility gap using low cost off-the-shelf devices. The contributions made by this paper include the following. First, expand the work done on pollution monitoring by previous authors to include noise pollution. Second, expand the work done by previous authors to include crowdsourcing. Finally, design and implement the environmental trends visualization platforms. The expanded crowdsourcing option will enable general public participation in environment monitoring based on an Android-based Yo-Yo OTG device connected to a mobile phone via Bluetooth. The main feature of the Environment 4.0 model is the use a variety of data collection sources for environment pollution monitoring, with the combination of static sensors attached to certain places in cities and mobile sensors on board automobiles. The entire system can detect the distribution of air pollution and noise pollution in real time. This fill the identified gaps in visibility. The entire system is adopted from the 4-layer IoT architecture. Each of the layers are described as follows. The system consists of two categories of sensors. First, static sensors, which are deployed in fixed locations around the cities and send data to a centralized server at set intervals, similarly to the proposed in the thesis of Shu Chen. Second, mobile sensors which are carried out around or attached to vehicles. These mobile sensors enable coverage of previously uncovered zones. For this work, we choose the lower one for our network layer, which is a type of LP1. They are characterized by low power consumption and low speed transmission and are well suited for non-demanding applications in equipment limited in resources and for which the battery life must be extended in the order of several decades. The application layer consists of three aspects which are so described. First, the sensor and communication hardware run a software firmware responsible for collecting and transmitting data. Second, server-based software belonging to the middleware layer and is responsible for receiving and analyzing data. Finally, web or mobile software of the application layer is responsible for displaying information to the end user. The validation of our approach was done by developing two prototypes of the system and using some scenarios to test the E4M in monitoring the air quality and the noise level in certain places of the city of Lubumbashi in Democratic Republic of Congo. Data from static collector. For this device, we carry out the experiment at 4 locations across Lubumbashi. Main readings from the MDB capture device is given in this table. Data from mobile collector. Similarly to the previous section, we conducted a different set of experiments by placing the MDB in a vehicle and slowly driving around the region of interest. 3 distinct locations around Lubumbashi were considered. To simulate the deployment of a LoRa one for the city of Lubumbashi, we use Radio Mobile. We consider 20 sensor nodes distributed across the city to measure pollution levels. In designing a user interface for our pollution monitoring solution, we created a web application using Django Framework, OpenStreetMap API, and CRUDGS tools to render interactive geographical data on different maps. The map shows the location of the sensors as dots of different colors classified according to pollution index. In conclusion, we say that our preliminary experimental tests were carried out according to relative comparison. We consider Golf Lido as a benchmark with clean air and low noise level to identify places with a 8 level of pollution in the city. We showed that participatory monitoring of the environment is feasible and makes it possible to cover the difference in visibility gap. The experiments carried out in this work are therefore part of the iterative deployment of ongoing research which extends in several different directions, for example, use of calibration techniques and the development of correction functions for sensor calibrations. Thank you for your attention.